Hello everyone. Today we'll be going over sulfonation and why you might want to do one. To start with, a sulfonation is an electrophilic aromatic substitution reaction that results in the addition of a sulfonic acid group to an aromatic ring, such as benzene or toluene or naphthalene. So the mechanism will be as seen. It will be like this. Sulfuric acid, and you will get, as your final product, you will get plus water. So, as you can see, one of the hydrogens that would have been here has been abstracted and replaced with the sulfonic acid group, and the excess hydroxyl group has been turned into water. So sulfonic acids are generally very strong acids, and you can use it as an acid catalyst in a Fischer esterification, or in really anything that requires sulfuric acid but needs to be slightly more selective. Also, the reverse reaction to get our beginning products back is very simple. You start with your sulfonated arene, and you add excess water comparatively to your sulfonic acid, and you reflux it, and you end up with your beginning products. Now you might be wondering, if water reverses this reaction, then you have to find a way to drive this water off, and that's where a special piece of glassware called a Dean Stark trap comes into play that works on high boiling azeotropes to help remove the water, which we will see later in the video. Sulfonic acid groups are also pretty helpful because of how large and bulky they are, and this allows them to block certain positions on an aromatic ring from being subject to an electrophilic aromatic substitution reaction. And this can allow a chemist to easily synthesize specific compounds and control specifically where a reaction will take place on this ring. So let's look at a specific mechanism real quick. So let's say we have toluene, and we want to get to dinitro toluene. We want to get to that. To get from this to this, you can't simply nitrate it, because if you were to just simply nitrate this molecule, you could get multiple products. If you just did a single nitration, you could get it in any of these three positions, and then if you let it run, you can't guarantee that these two positions will line up all the time. You could get it like this, and that's not what we're looking for. And if you let it do a triple nitration, it would look like that, and that's TNT, so you don't want that. So to do this, we can sulfonate first, and so H2O SO4 plus some heat, and since the sulfonic acid group is too big, it can't go here and it can't go here, because the steric hindrance between the sulfonic acid group and this would be too great, because it's too bulky. So the only place it can go is right here. So now we have this spot blocked off, but we also have these two spots right here blocked off from being substituted because of how big this molecule is. It's blocking off these two areas. And since this is, so it wouldn't matter because these two are the most highly activated, since this is a deactivating group and this is an activating group. So so this would, so, but still, hindsight, you know, if there was something that was activating these two positions, they wouldn't be able to go there. So now we can nitrate this and do a runaway nitration. So both, it gets nitrated twice. Oh, it would appear I've run out of room, but then obviously, let's just flip this over. You would reflux this with excess water, and this and the sulfonic acid group would come off, and you would have your end product. So as you can see, this is a very useful technique to know if you're trying to be very specific about how you add groups onto a molecule, because it saves you the hassle of having to separate all these based on their different qualities, you know, because I'm sure, like, DNT, the derivatives of DNT all have different polarities and stuff, and there's probably some way to, you know, separate all these mishmash of different nitrated toluenes, but this is easier, and I'm sure you get a higher yield like this. Even though I've never done it, I can probably guarantee you would get a higher yield like this. So for today's video, we're going to be making paratoluene sulfonic acid, which is just, as you saw before, the sulfonated version of toluene. It's also known as just PTSA for short, which is probably what I'll be calling it because it's a long word and I don't want to say that. And it is actually one of the few strong acids that is a solid at room temperature. So, and you can use it as an acid catalyst or in this mechanism that I just showed. So, oh, also, this is the procedure that we're doing this from is from a Doug's Lab video. The link will be in the description if you want to check it out. Well, let's go get into it. Hello everyone. Alright, so just showing you real quick the ingredients we need. About 150 milliliters of the toluene we purified in the last video, and about 15 milliliters of sulfuric acid. I'm using drain cleaner again, and we're going to be doing it in a 1-to-10 ratio. So whatever we have of this, we're going to take 10% sulfuric acid. So 150 milliliters, 15 milliliters. And now I'm going to put them both into here. And then I'm going to set up the Dean Stark trap, and I will show you that once it's done. And add a stir bar. Slowly we're going to add the sulfuric acid. As not to generate too much heat. And then I'll figure out how to set up the Dean Stark because my stands don't really go tall enough, as you might be able to see. If these don't really go tall enough, so if I put this on here like that, then the reflux condenser, I don't know if it's going to be high enough. So I'm going to figure that out and I'll be right back. Okay, so here's the Dean Stark trap. So we're going to reflux this, and anything that boils off is going to come up here and will recondense up at the condenser and come down into this. And now, since toluene and water have a high boiling azeotrope, they will come over together, but then once they come in here and cool down, they will separate out into two layers, water obviously being on the bottom because it's more dense, and it'll settle out on the bottom, and toluene, eventually when it fills up to the top, it will drip back down. And so we have a feedback loop. And if need be, if there's too much water that the water starts to drip back, we can let the water out with this little fancy nozzle. Make sure it's closed, obviously. It's right. That's closed. We don't need it dripping out while it's refluxing. That wouldn't be good. So this needs to reflux for about 4 hours, or when anything stops coming over. So I'm gonna start the reflux, and then about like halfway through I'll show you what this looks like. And because honestly, this is gonna be the first time I've ever done this too, so this is gonna be a first for me. And we'll see the high boiling azeotrope in action. All right, let's get it going. Stir on the stirring. Let's turn on the heat, and let's see what happens. All right, I'll be back. I'm back. For some reason, the reflux was having some difficulties getting over this arc after this filled up all the way, so I had to raise the temperature a little bit. I'm gonna raise it a little more right now, and it's filling up again. So you can see the steam kind of filling its way up here, and I'm gonna try and get a shot of any water going down this. So as you can see, this upper layer right here is the toluene, and this lower layer right here is the water. And now if this water starts to exceed this volume, we can just drain it down into this beaker, which I doubt will happen, but let's see if we can get a good shot of any water vapors, any water droplets passing through the toluene. It would appear at the moment that it's still having some issues with the reflux. So we're back. This has been refluxing for about like an hour and 15 minutes. Well, roughly, because I had to raise the heat because the vapor front for some reason was stuck about here. I don't know why. I think my heat was a little too low, and after a while it had trouble getting over this arc, because it's slightly cool out today. It's like 80 degrees Fahrenheit. So yeah, so I had to just raise the heat, and now it's going at a reasonable pace again. So as you can see, there is dripping out of the condenser, and it goes back down and into the flask, into the reaction vessel, and then any excess is being collected over here. There's the toluene layer, this big, thick, clear layer right here, and this little layer right here is the water. So these are brought over together as a high boiling azeotrope, which just means that they co-distill, similar to like a steam distillation to bring over an oil when it boils over with water, and the water's vapor carries over the oil with it. Something similar is happening. The toluene is coming over with the water. And this is a way to remove water from this reaction, as water, as you can see, is a byproduct of this, and it will actually break these bonds and form toluene and sulfuric acid again. So we want to get rid of water. Now let's see if we can get a shot of a water droplet rolling downwards. I want to see if we can get that. I don't think we're going to be able to get it, which kind of sucks. But if you go to the Doug's Lab video, you'll see it there. Kind of annoying that you can't see it on this, but my phone's quality is kind of trash, so what are you gonna do, you know? I guess it happens. So I'm gonna let this reflux for around I think 2 more hours, and then I will be collecting the crude product from this. And to do that, we're going to be just pouring it into a beaker and adding some distilled water, because this is currently the anhydrous version here, and we need the monohydrate because it is insoluble in water or toluene. My bad. And it will crash out. I don't remember off the top of my head if it's insoluble in both or whatever. So it will crash out of that, and we'll be able to vacuum filter it, and then we will be able to purify it further by putting it in a water bath and melting it and allowing any excess toluene in water to boil off. All right, so just get a last shot of that. It's pretty cool. Interesting little piece of glassware. I don't really know what other. Oh! Did you see that? Did you see that big glob of water that just flew down there? Oh, I hope I got that. It was big. It went all the way down. Darn. I'm gonna try and get a shot of the water, and I'll be back. So you see that little bubble right there? Oh, there goes a water drop. See that bubble right there? That's a big glob of water. Let's see if I did this with another one. I flicked it, and it caused it to slide down. But for some reason, some of them, they get stuck on the glass. I don't know why. I don't know what's causing that. I guess some kind of hydrophilic hydrophobic interaction causes them to, oh, there goes another one, to get stuck on the glass. Strange. So as you can see, there's about I put this on the wrong way, so it's hard to tell. 3 milliliters. There's about 3 milliliters of water collected so far in about 2 hours worth of reflux. So that probably would have substantially impacted our yield. And I think we have 2 hours left for this reaction. I'm excited to see how much product we get from this. It should be interesting. Okay, so we just finished the reflux. So now I'm gonna take the reaction vessel and I'm going to pour it into this 250 milliliter beaker. It's volatilizing a lot of toluene vapors, but that's okay. Woo, that's hot. That's a hot tamale right there. Let's get that back in the clamp. And now we're gonna add 10 milliliters of water, distilled water, to crash out the anhydrous paratoluene sulfonic acid into its monohydrate form. And we're going to stir it. And as you can see, there should already be some crystals forming at the bottom there, if all went according to plan. Yes, there's some crystallization occurring. And we're gonna let it cool now. And, yeah, there's some crystals forming on the sides, as you can see. And then, so we'll let this cool, and I'll come back once it's cooled off. All right, see ya. So this is it after a minute or two. As you can see, it's formed some nice, large, clumpy crystals because I put the water in when the solution was still very hot, which causes larger crystal formation and will hopefully keep it more pure. And I'm mixing it to allow more water. And all right, let's see how much more forms. Okay, so it's fully crystallized, as you can see. Okay, so as you can see, some large, flaky chunks of paratoluene sulfonic acid crystals precipitated out. I started vacuum filtering this, but there was some technical issues. So let's try this again and see if it actually works. Okay, that's better. So now let's just scoop this all in there. Scoop as much as we can in. And we're gonna let it sit on vacuum and dry out as much as possible. And then I'm gonna store it for the meanwhile, and I'm gonna finish off the purification of this by re-melting it on a double boiler tomorrow. Which should be interesting. They say you need a vacuum desiccator for this, but I don't have one. And apparently just using the double boiler is good enough to get it to a slightly technical grade. So that's fine by me. All right, so we're just gonna let it sit for now. And as you can see, we got a fair amount of crystals. All right, that's it for now. Okay, so what I have set up here is a little double boiler. I've got a pot full of water and I'm boiling it, and then the steam will come and settle on this glass and heat it up, and that'll cause these crystals to melt, and any toluene that is left in here and any water will boil off. So once it starts to melt, I'll take another video. So here's the crystals now that they're melted. I'm pushing them around with this glass stir rod, and I'm probably gonna let them sit like this for a couple of minutes. Yeah, it's starting to liquefy, and I'll let it sit like this for a couple of minutes so any excess water or toluene gets evaporated, and then I'll turn off the heat and I'll let the acid recondense and solidify, and we should have pure crystals then. As you can see now, the crystals are fully liquid. It's beginning to simmer a little bit. It's most likely any toluene or water being boiled off. And yeah, so that's about it for this. That's all you really got to do. You got to keep pushing it around and let all the water and toluene evaporate. I turned the heat off, and now it's beginning to solidify, and it's turned into this goofy semi-gelatinous mass. And so we're just going to keep moving it around until it's fully resolidified, so that any excess toluene gets pushed out. It reeks of toluene right now, so I guess that means we're doing it right. I'm glad that this worked, because I didn't have any other way to perform this. So it should be good. I'll come back to you when it's fully solidified, and we'll weigh it and see how many grams we got. So here we are with our end product. a nice white lumpy crystalline mass. We got 35.75 grams. That's pretty decent. So I have no use for this at the moment, but if anyone wants to recommend something I could do, I'd be obliged. So yeah, nice. It's a little grayish in some parts, probably due to some impurity. Not quite sure what. I could recrystallize it, but since I have no use for it at the moment, I'm not going to. I just did this for no particular reason, but that's okay. But well, thanks for watching the video. I hope you enjoyed. Hope it was informative, and have a good one. Bye-bye.